So again, a warm welcome to everyone for this webinar in the series of risks in outer space. And well, today it's a pleasure to have with us Christina Plainaki. She's again one of the young representatives of our community, and I really like this idea to have a mix of senior and younger scientists with us. Christina works at the Italian Space Agency. She's a specialist in the interaction between planetary surfaces and the space environment in terms of radiation bombardment by plasma. And she's been working on different bodies of the solar system, Ganymede. And now she's heavily involved in different missions, in particular Juno, the ongoing NASA mission, but also JUICE and Bepi Colombo. And today she'll be addressing, well, topics she's working on it, namely the interaction between the space and planetary environments, in particular, with a particular focus on Jupiter. So let me just remind you, if you have any questions, feel free to ask them, write them down in the chat, and we'll be addressing the questions as they come at the end of the presentation. So if you have any questions, please write them down in the chat and we'll go through them at the end of the presentation. With that, Christina, I think I let you start.
Okay, thank you, Thierry, for the presentation and for this invitation to participate in this interesting series you have been organizing the last years in EC. So, hello to everybody. Today I'm going to discuss some topics related to planetary space weather science in the context of solar system exploration. So briefly, this is the outline of my talk. After a brief introduction on some basic idea behind what we call planetary space weather, and on the motivation why we do these research activities related to this field, I will pass to discuss the traditional concept we have for planetary space weather. And then I will move outwards in the outer solar system to focus on the Jupiter system and discuss some recent results regarding space weather phenomena in the Jovian system. Finally, I will present some concluding remarks. So, space weather is the physical and phenomenological state of natural space environments, as we all know. And there is a discipline of planetary space weather, which, similar to the discipline of circum-terrestrial space weather, aims at observing and understanding and predicting the state of the sun, the state of interplanetary and planetary environments, their disturbances, and the impacts that these disturbances can have on biological, technological systems. Also with the scope, of course, to provide countermeasures, alerts, and protection strategies. So one can easily understand that when we come to science, the space weather conditions around a planet or a moon within a planetary system are strongly related to the interactions that has this environment with the outer space. So with this in mind, we can easily understand that the phenomena related to planetary space weather cannot be disconnected from the variability. Temporal or spatial variability, either of the solar activity, and this is the case of the inner solar system, or the variability of the plasma, of the energetic particles within a magnetospheric system, and this is the case of the giant planetary systems of our solar system. There are several reviews on planetary space weather giving and discussing the global picture. Here is a limited list, and of course not exhaustive, of some papers in this field. So why do we care? From a scientific point of view, we need to understand the physics that build the space weather. We need to test theories and or scenarios for the various mechanisms that are in action. And we need to bring our current models to their extreme limits. And to do this, a cooperative science approach is usually a very good way to get the global picture. but also in the context of solar system exploration, to correctly interpret the obtained scientific data we have from various missions, scientific missions in the solar system, we need to know the exact conditions under which these observations were taken. And there are several examples in literature of data which were noisy or had some problems due to an ongoing space weather event in the background. So it is really important to have a knowledge of the space weather background of the environment we are studying and observing. And also we need the planetary space weather to better understand the circum-terrestrial case of space weather phenomena, having in mind the whole picture. From a technological point of view, also we need to develop and test and validate forecasting tools to keep space component and satellites safe, or at one astronomical unit or even at other distances from the Earth. And to do this, we need to advance our current predictive capabilities, and to better address such an objective, it would be good to be based on the best science available. So we need to look outside our own planet. We need to see the mechanism in a larger concept, in a larger landscape, let's say. And also in view of solar system exploration, we need to design spacecraft that are resistant to extreme space weather conditions, but also payloads and components on these payloads. So this is the classical picture we all know from space weather phenomena resulting from sun-planet connection and its interplay with the galactic cosmic ray flux. And this is a picture that is applied to the inner solar system case. And here you see the Earth and the Sun and various sources of space weather like flares and CMEs, also interactions between solar wind streams of high and slower velocity. And you see all these other mechanisms that take place in between the Sun and the planet, that, for example, propagation of the various disturbances like CME propagation, which results also in particle acceleration. And then we have a series of phenomena that take place near the environment, the planetary environment. The effects of space weather on, for example, magnetospheric dynamics or radiation belts variability, but also effects on the atmosphere and ionosphere. And sometimes we see also secondary effects of space weather on the ground. This is the case of ground level enhancement events, for example, but also underground. And of course, there is a whole field that studies the effects on avionics and communications of space weather, and other effects, biological effects, for example, on the astronaut safety. So as you see here, space weather is an inter and transdisciplinary challenge, and many different topics are interested, starting from solar physics, solar terrestrial physics, ionospheric physics, geomagnetism, but also a big field of study is the technological and biological impact of space weather on components, and but also on the safety, on the health of our astronauts in the International Space Station. And one in the inner solar system can easily imagine in the place of the Earth other planets. And here you see Mercury, which has a relatively weak magnetic field, but very dynamic. It is the planet that is closest to the Sun, so it's a very good position to study extreme space weather conditions. And Baby Colombo, which is now in its cruise phase, will investigate this process in Mercury. And you can imagine also Venus, a body without an intrinsic magnetic field, but with a strong atmosphere that creates an induced magnetic field. And also Mars, a body of a special interest, also in view of human space exploration. But today I'm not going to talk about the inner solar system case and space weather in the inner solar system. I would like to touch some arguments that are a little more exotic, and I would like to focus on the outer solar system. So when we refer to space weather phenomena in the outer solar system, we analyze, we study phenomena that take place in the circumplanetary environment of a giant planet, for example, upper atmosphere, radiation belts, rings, or in the environments around the moons, for example, exospheres of the moons or atmospheres, or even in the case of Ganymede, as I'll show later, even magnetospheres within the giant planetary magnetospheres. And here on this slide, you see the 4 giant planets of our solar system, the gas giants, Jupiter and Saturn, and then the ice giants, Uranus and Neptune. And I would like to note here that the space weather conditions within a giant planetary system depend mainly on the properties of the system itself, contrary to the inner solar system case, for example, that the sun is the main source for space weather phenomena. Of course, the magnetic field plays a very important role in the evolution of all the space weather phenomena that take place in these environments. On this slide, you see the strongly magnetized bodies of our solar system, Jupiter, Saturn, Earth, in the first line, that have a magnetic field that it is tilted up to 10 degrees from the spin axis. Whereas on the second line, you see Uranus and Neptune, which are bodies that have irregular magnetic fields, strongly offset. You see the lines do not even circle the planets. The magnetospheres are very irregular. And also from this slide, you can understand that in the solar system, we have very different magnetospheres and a big range of temporal and spatial scales. So very different bodies. But also the plasma and the particles within these systems plays an important role. Here, just to show you the very nice figure by Frank Bagenal and Steve Bartlett on the size of the magnetospheres of the solar system, scale to the radius of the planet, and you see the dominance of the magnetosphere of Jupiter, which is currently investigated by the NASA Juno mission, and I will talk about this in the next slides. So planetary space weather, where to look for? We can look for phenomenon in space weather phenomena in the outer planets, in the magnetospheres, in the upper atmospheres, ionospheres, but also surface-bounded exospheres. For example, in case of moons embedded within the magnetospheres. And also we can search for space weather events inside atmospheres and at the ground. So to study this kind of phenomena, modeling is a strong tool for us for understanding the underlying physics. But of course, we also need observations. Multi-point observations is the best way to go forward. So I pass now to the main focus of this talk, which is Jupiter, the Jupiter system. So here you see the magnetosphere of Jupiter. And as I said before, the space weather phenomena that we expect to study, to see there, have their origin in plasma and energetic particle sources that are located within the system. So Jupiter has a very strong magnetic field with an intensity in the equator of the surface of the order of 7.8, 10 to the 5 nanotesla, and the dipole is tilted by almost 10 degrees. And we have different plasma sources. The most important one is the volcanic activity of Io, the closest one of the 4 Galilean satellites that you see here on this picture. Io is a volcanic satellite. Europa, Ganymede, Callisto is what we call the icy satellites. And we have also some contributions in the plasma. We believe we have some contributions from the atmosphere, tenuous atmosphere of Europa and Ganymede. But this is still, of course, to be confirmed with the future measurements. And another thing I would like here to point out is that the plasma sheet that you see in red in this slide is tilted, of course, with respect to the rotational plane of the satellite. This is very important in order to understand the mechanisms that take place. And here I focus on Ganymede. Ganymede is a very interesting body from the planetary space weather perspective, since it is the only moon in the solar system that possesses an intrinsic magnetic field. It is not a strong magnetic field. It has an intensity at the equator on the surface of about 700 nanotesla, which is stronger than Mercury in any case. But this field reconnects with the Jovian field, as you see on the slide on the left. Here on your left is the plasma direction, so it's the plasma upstrip region, whereas on the right is the plasma downstrip, and you see the effects of tail reconnection. Just let me also notice that the plasma has a velocity that is much bigger than the orbital velocity of the satellite. So it practically overtakes the satellite, but due to the magnetic field that Ganymede possesses, there are created preferential regions for the ion entry, and this determines the morphology and the properties of both particle precipitation and also auroral emission. And on the right, you see an example of auroral emission. This is the 1,356 angstrom emission. This figure is from McGrath, 2013, and this is due to the electron impact dissociative excitation of molecular oxygen. So this auroral emission was also an indicator of the underlying tenuous oxygen atmosphere of Ganymede. Of course, these phenomena are very variable in time and in space, as it has been demonstrated. So we're very interested to understand the revolution, for example, to be able to identify the conditions during future in situ observations in the system. And to let you better understand this perspective, I would like here to show you Ganymede, which is orbiting around Jupiter. And you see also the Jupiter plasma sheet, which is tilted, as I said before, with respect to the rotational plane of the Moon. And this means that along its orbit, Ganymede passes from regions in the plasma sheet where it is near the center of the plasma sheet. In other parts of the orbit, Ganymede is above the center of the plasma sheet, and in other parts of the orbit is below. And these conditions were similar to the ones that were met by the Galileo mission in the 90s, the mission of NASA. And we have several data from that mission, which helped us to understand the environment around Ganymede. And some flybys characterize these conditions here indicatively. I put into this figure the G2 flyby of Galileo, where Ganymede was above the center of the plasma sheet. The G28 flyby, where Ganymede was below the center of the Jupiter plasma sheet. And during the flyby G8 was near the center. And to understand better how ions were circulating during these conditions, we modeled the ion circulation. We used as an input spectra and for the ions from the Galileo measurements. And we used also a magnetic field model taken from the MHD model of G et al. 2008 and 2009. And here, as you see, it's an example of how the environment is expected to be. Here, this example refers to 30 keV oxygen ions. For these three different conditions, you see the intensity is different in each case, but also the morphology and the precipitation of these ions to the surface is different. So this motivates us to understand also how critical and to address how critical is the observation of the altitude of the observation for understanding the potential effects of space weather on the surface of Ganymede. So to do this, we did our simulations for two cases, for ions precipitating on the surface, and this is the figures on your left, for the three different conditions, different configurations of Ganymede with respect to the Jupiter plasma sheet. And we repeated the same calculation for the altitude of 500 kilometers. Again, we use as an input the model of G et al. 2008, 2009. We very recently published this data, and we see here that our simulations showed the results, showed the effects, for example, of the Taylor connection. And as you see here, of course, the effect is stronger on 500 kilometers, whereas on the surface, the moon is more shielded. And we investigated also the role of energy. And here on this slide, it's again sulfur ions, highly charged. On the left, initial energy is 30 keV. On the right, 300 keV. And also here, the Taylor connection results in the precipitation of ions in the low latitude leading hemisphere. Just to mention the coordinates here on longitude, these are the west system coordinates. So 90 is the leading hemisphere apex and plasma downstream. And Jupiter is at longitude 0, and at the 270 is the apex of the trailing hemisphere, so the plasma upstream hemisphere. So also here you see we saw in 30 keV an increased flow in the anti-Jupiter low latitude equatorial surface regions, and this is noticed in all configurations, of course, with different intensity. The morphology is slightly different. And in the end, all this work was motivated by our curiosity to understand how space weather can have long-term effects, can have effects on what we call weathering of the surface. So for addressing this, I show you here the different configuration between heavy ions on the left and light ions of the same energy on the right. And also from this figure, you can understand that, of course, higher rigidity ions have more access to more regions in the moon surface with respect to the lighter ones. And as you see here, the precipitation is asymmetric, and there is an anti-Jupiter increased flux, and this was found from our model, but was found also from other models. For example, the Fatemi et al. Model, which is a hybrid model, not a single particle one, as our own case. And all these features can be related also to observational features, for example, of the brightness of the surface. Similar results were found also by Lutz et al. In 2020, who did some simulations to understand the flow of electrons and the actual precipitation on the surface. And also there, these authors found that at the high energies, 450 keV, the electrons do not have access at some certain parts near the equator of the surface, and nearly 60% of the moon surface has in nearly 60% of the moon surface there is no electron precipitation. So we did our calculations for the ions using sputtering rates and yields from literature, and we repeated these calculations for all the different configurations, and we averaged these rates, and we found out that there is a net loss of mass due to sputtering from Ganymede of the order of 1.3 kilograms per second, which is much less than the one calculated in the past, for example, for Europa, which is highly bombarded for radiation in Jupiter. So this was an exercise we did using data from the past, but currently Juno is registering very important data for the Jupiter system. And in particular, these are some first results published in Paranikas et al. 2021 regarding the particle environment. Here is hydrogen on the right and electrons on the left. And this environment, this energetic environment, in reality stimulates a lot of processes on the surface of Ganymede, which is Ganymede has no substantial atmosphere, has a sputtered tenuous atmosphere. It's mostly an exosphere, and with some local enhancements due, for example, to ice sublimation. And in any case, this absence of atmosphere allows the ions to directly impact the moon, especially in the regions where the magnetic field lines are open. And several processes take place, like sputtering or radiolysis stimulated by radiation, and neutral particle release and exosphere generation, whereas other molecules, like oxygen molecules, bounce several times once they are generated through radiolysis, and they create this thin envelope of molecular oxygen. And we have some pickup processes of this tenuous atmosphere and some charge exchange. And as you can understand, there is a live and a dynamical mechanism of exchange of material between the Jovian magnetosphere and Ganymede. So it is important studying space weather near Ganymede is important also for understanding the real relation between Ganymede and its parent planet. And here, just to show you the exosphere of water on the left, which is much influenced from the morphology of the ion precipitation, whereas the molecular oxygen exosphere on the right is a more homogeneous one, since the molecules there, in some way, they lose memory of their initial, let's say, generation due to the multiple bouncing on the icy surface. But I do not have so much time to enter more in detail on this. I would now like to show you some results from a mission from NASA's Juno mission to the Jupiter system. So Juno is an innovative planetary exploration mission of NASA to study Jupiter. It was launched on 5 August 2011. It arrived at Jupiter on 5 July 2016. As you see on the right part of this figure, Juno is a spinning solar-powered spacecraft. It performs one rotation every 30 seconds, and it has a highly elliptical orbit, which allows to avoid the radiation environment. And this orbit extends from above the top of the clouds up to the far magnetosphere and back to Jupiter. So the duration of the orbit during the prime mission, which ended in July 2021, was of the order of 53 days, whereas during the extended mission after July 2021, the orbit was evolved. There was a northward progression that allows us also to better study, for example, the atmosphere from lower altitudes, and to focus also on other aspects of the Jovian system. At this point, I would like to say that it was the first flyby of Ganymede on 7 June 2021 that marked the transition of Juno from a Jupiter dedicated mission to a real Jovian explorer. So Juno has several scientific payloads, very important for addressing various scientific objectives. On this slide, you can see these payloads. We have particle instruments, JD&J. There's a magnetometer, of course, the microwave radiometer, and the JunoCam, and the UV instrument, and the wave instrument. And among the various payloads, our agency has coordinated the efforts for the two experiments of Italian leadership. I'm talking about the Jovian, the infrared spectrometer experiment, GIRAM, which is under scientific leadership of INAF, and the gravity science experiment, which is under scientific leadership of University of Rome, La Sapienza. So these instruments have already provided important data and have done many new discoveries on the Jupiter system, and many of them are very much related with planetary space weather aspects. Some words about the GIRAM instrument. So the GIRAM, as I said before, is an image spectrometer. It has its heritage at the Virtis spectrometer for Rosetta. It was developed by the Leonardo industry here in Firenze, and the infrared detectors were provided by Raytheon. So GIRAM in reality is equipped with a single telescope, and it includes an infrared camera and a spectrometer. In reality, the camera has two color filters that are to observe both thermal emission of the planet And this is done through the measurements of using the M filter that it is focused in between 4.5 and 5 microns, and the L filter, which is dedicated to the investigations of the auroral emission of Jupiter, which is centered to the range 3.3, 3.6 microns. So there is a very good resolution of about 0.001 degrees per pixel, which is translated, for example, to the ionosphere mapping at distances of about some tens of kilometers. And the spectrometer also is very important since it provides measurements in the range between 2 and 5 microns with a sampling stack of 9 nanometers. And at its Juno rotation, GRAM acquires simultaneously either the M or the L image, not both, and can obtain, of course, a spectra at 336 sampling points. So today, since I talk about space weather, I will talk about the H3 plus aurora Jupiter. So H3 is produced when H2, the H2 atmosphere is ionized by energetic electrons. And then it reacts with a neutral hydrogen and it produces H3 plus in a rotovibrational excited state. And the excitation produces the infrared emission in 3.3, 3.6 range, microns range. So this is almost in thermal equilibrium with the neutral atmosphere, and the spectrum of the emission depends on the local temperature. So if we have the GRAM measurements, we have an instantaneous picture of the particle precipitation processes as it happens in the UV, and we monitor the H3 column density and temperature. So GRAM in these years has monitored the infrared auroral activities, as I will show you in the next slides. So here you see the South Pole. This is a figure taken in 2016. The measurements were taken in 2016. And is the emission due to H3 plus. On the left, you see an enhancement in the dusk region. We're in the southern hemisphere. And if you see the right figure, we have the spectral color ratio between 3.5 microns and 3.7 microns, which is diagnostic of the temperature. Blue, it's cold, red is relatively hot. Take into account that here we talk about a range between 850 Kelvin and 1100 Kelvin almost. We are in an altitude between 500 and 700 kilometers from the zero level, which is defined the level of 1 bar pressure. So the thickness, of course, is quite variable. So we are very interested in taking these pictures at during different periods to understand the variability and potentially to correlate this morphology in the future also with other aspects, for example, the morphology of the film. So here another aspect that I would like to discuss in this presentation regards the Io-induced aurora on Jupiter. So Io, as I said before, is the innermost Galilean satellite, a volcanic satellite, but all the Galilean moons that orbit Jupiter are swept by the magnetic field. And this creates perturbations that can travel along the field lines as advent waves. And sometimes they can be reflected also due to density gradients. And they are able to accelerate electrons towards the planet, producing satellite-induced auroral emissions that are known as footprints. These footprints are identified equatorward of the main auroral emission as a series of bright spots, followed by an extended footprint tail. And here is a figure that I would like to show you. Here it was taken on 1st September 2017. And here, this is the South Pole, and with the blue arrow, we indicate the main spot of the Io footprint, and you see it has an oval shape, and it is kind of offset with respect to the predicted positions that you see in the blue dotted line. And you see also the extended tail of this figure. And this tail has a particular morphology, and it's currently being investigated. And you can see some more details on this on our science paper of 2018, Moore et al., and also in the paper Moirano et al. GRL in 2021. So at this point, I would like to say that GRAM is currently providing the largest database of Jupiter auroral footprints with the best spatial resolution to date. So this is very important for future studies that can correlate several aspects from the images up to the particle precipitation, and using also potentially modeling tools within. So this is another very nice image. This is the Io footprint tail observed in 27 August 2016 at about 100 degrees behind the main spot. The tail consists of two separate arcs, as you see here. We understand that these morphologies resemble in shape the motion of an obstacle in a fluid. But still, we do not have a clear explanation of how this happens. We know that Alfvén waves are in action. Alfvén waves directly generated by the satellite, and they're responsible for the main, for example, spots in the tail. We have also Alfvén waves that are reflected due to density gradients. And we have also electrons that are bouncing between one hemisphere and the other. And there are several mechanisms that are proposed. Some of them explain some figures, in some others there are some drawbacks. So this is a very hot topic, and it is still the questions are still open, and there is still work to be done also with the precious help of the Juno data of these years. So to conclude, Juno is currently providing us a new and revolutionary view of the Jovian magnetosphere and the particle environment. Here on this talk, I had the chance to talk only of a few of the important discoveries of Juno, but you can find some more material, of course, in literature, but also in the mission's official site. The mission is led by Scott Bolton in the Southwest Research Institute, so you can find things in this site that you see on the slide, but also on the NASA's official site for the mission. And to conclude, I would like to say that Jupiter will be investigated also by another mission, which is the JUICE mission of ESA. It is dedicated to the exploration of the emergence of habitable worlds around gas giants, to the study of the Jupiter system as an archetype. But among the various science objectives that I don't have the time to analyze and discuss separately, I would like to point out that there are some objectives related to planetary space weather, and these regard the investigation of the exospheres of the icy satellites and the study of Ganymede's intrinsic magnetic field and its interactions with the Jovian magnetosphere. And we are looking very forward to the launch of JUICE this April, and we'll have the chance to return to Jupiter after Juno and complete our investigations with new data in the years to come. So I would like to conclude my presentation of today, some general remarks regarding planetary space weather science and its importance. So understanding planetary space weather in the solar system, of course, is a scientific challenge. We have data in our hands from numerous past missions and ongoing missions, but we have also modeling tools. And it would be important to begin to see things through a comparative planetary science framework and a multi-point data analysis approach, if possible. To address the various science objectives of more than one mission, sometimes a synergetic approach among missions in research is necessary. And this, of course, can benefit from theoretical and data-driven modeling. And of course, of continuous update and continuous interaction between the communities, between different missions. And then planetary space weather science is intrinsically inter and transdisciplinary, as you can understand, investigating the processes of space environment interactions at different distances from the sun, but also within a planetary system, can help to better constrain the models we have in our hands today, also for the circum-terrestrial space weather, because we have the chance to study the same phenomena, physical phenomena, but under completely different conditions, even extreme in some cases. And this, in the future, will help us to make more accurate predictions of the environment we need to study, for example, in the context of exploration. So to get the global picture and to significantly advance scientific knowledge on space weather, we need new space and ground-based measurements, possibly from different locations within the solar system. Of course, the outer solar system is a fantastic place to study, very intriguing, very different phenomena. We have the chance to study very different and extreme phenomena in these systems. So this will help us to significantly push our current space weather models to their limits, and this to better understand the related physical mechanisms in action, with a positive impact also for the case of the circum-terrestrial space weather. So knowledge in the end of planetary space weather conditions will allow a better planning of future spacecraft orbits, observations, and operations. And with this, I would like to thank you all for your attention.
Thank you so much, Christina, for this nice talk. Thank you very much. So, oh, please don't run away.
Yeah, sorry.
No problem. So now we have some time for questions. If you have questions, please don't hesitate to write them down in the chat, or you can also raise your hand if you wish, and I will open the mic so that you can ask your question directly. So there was someone who raised his hand or her hand. I don't know. It's in Japanese, so it's a katakana. I guess it's Tomako, probably something like that. If you could turn on your mic. The person who has his name in katakana. Can you please turn on your mic, open your microphone?
It's muted.
It's still muted. Okay, well, if not, then maybe you can write your question in the chat so that we can proceed. So the next question is by Andrew Coate. Hi, Andrew.
Hi, Andrew.
Did you ask the question directly? If you can unmute your mic.
Yeah, can you hear me?
Yes.
Hi, Christina. Very nice talk. Thank you. And yeah, but the question was at Ganymede, there's another space weather effect, which is the aurora. And I wondered if, this was seen with HST, and I wondered, has this been looked at any more with modeling or perhaps with Juno?
Yeah, thanks for this important question. Yes, of course, with modeling, it has been seen in the past, and also with Hubble Space Telescope, there have been some more recent campaigns by Lawrence Roth. Some nice review has been included in the recent book, Cambridge Press, if I remember well, on Ganymede, the Ganymede book. There was a chapter that touched all these arguments, and Lawrence Roth had provided a very nice review of the available observations also for the aurora. With Juno, I guess it's been studied. I'm not very familiar with the work of the UVS team, but what I would like to point out is that yes, the aurora observations are very important also for the aspects that I discussed in this presentation. Since, as I showed in one of my slides, the system in Ganymede is very complex and and various mechanisms are interconnected. So you have the particle precipitation, insertion through the magnetic field, the open magnetic field lines. They generate this tenuous exosphere, this tenuous atmosphere. And then you have also the precipitation of the electrons that activate the aurora emission that we saw in the UV. Was the main as far as I remember, the main process was the electron impact dissociative excitation of molecular oxygen. So these observations have been also very important as an identifier of the type of atmosphere, of tenuous atmosphere we expect in these moons. Yes, please look some reviews in the Ganymede book, and of course literature, the recent papers by Lawrence Roth and team.
Great, thank you.
So we have another question by William Wall. If you can unmute your microphone, about what did we learn since Juno?
Hi, am I coming through okay?
Yes, it's working.
Yeah, when you say that Juno has revolutionized our understanding of the Jupiter system, could you be more specific, give us specific examples of what we know now that we didn't know before?
Yeah, of course. For example, as I showed in the talk, I start from my own topic. We didn't know about the morphology of the footprints. We didn't know about the tails, the double tail we saw, for example, for Io. We didn't know all these very detailed morphology for the Io footprint, but also for Europa and Ganymede footprints. I didn't talk during this presentation, but we have also very nice figures taken with GRAM with a high resolution that has never been seen before. Moreover, if I can mention some other topics that do not interest directly, let's say space weather, for example, the study of the atmosphere. We had views, of course, that we could never have from ground-based observations of the poles. We discovered Juno always through the GRAM measurement, but also through the microwave radiometer measurements, discovered the circumpolar cyclones, which are other figures. So we have these cyclones on the poles that change during various periods. We see some of them disappear and come back, and we saw this structure that we never had in our minds that could be there. Then, for example, I also remember a very, very important result that regards the core of Jupiter. We now know that from the gravity measurements that there is a dilute core of the planet. We know that the magnetic field, for example, is very asymmetric. There is the famous blue spot, which is a region near the equator of increased intensity. And we know that the winds and the velocity of the winds in the atmosphere are strongly related, for example, with the structure of the magnetic field. These are some things that come to my mind like this. There are several papers out on the discoveries of Juno, and I don't think we will stop here, since now during the extended mission, we have also the chance to observe even more the satellites. For example, recently there have been some important papers on Io, on the volcanic activity. We will see once again Ganymede. We had the Europa flyby last October. Things keep coming up all the time. I mean, in my opinion, it is really a revolutionary mission.
Thank you.
Okay. I have a quick question related to what you just said. There have been these very recent results about Io, about the different composition of the atmosphere during the different types of volcanic activity. What will be the impact of these results on the interaction between this moon and Jupiter? Or maybe it's a bit early to...
No, it's a very, very nice question. Yeah, of course, what I can say is that through the experiments on board Juno, we will have the chance, yes, to others also the composition, because we have, for example, the spectrometer, the infrared spectrometer, GRAM can see the species. Of course, combining different observations from the Juno instruments, we can obtain even more information also on the, let's say, also on the variability of these features. In in my opinion, to connect this variability with the potential impacts in terms of contribution in the plasma sheet, we need, of course, to analyze well and in detail also the particle measurements, what we have right now, and of course the magnetic field. Yes, it is these are all features and mechanisms that are interconnected. Maybe we need also some modeling effort, which once the data will be more and the data set will be more complete, we will also have the chance to guide better our empirical or theoretical models to understand the interconnection. There's been some important work on modeling also based on ground-based measurements in the past for IO. Okay. But of course, with the new data, we will have the chance to go into some more detail on this, for sure.
So I'm just telling people, if anyone has questions, feel free to write them down in the chat or to raise your hand. I had another one, and in the context where there are plans to revisit or visit the outer gas giants in our solar system, what did we learn in the last decade that may affect the way we want to investigate or just program the orbits around these planets in order to focus more specifically on certain aspects we didn't know about and we have learned by studying Jupiter?
Yeah, of course. Okay, if we need to return to Jupiter, for example, we now have a broad set of parameters, and we can better set the limits from a technological point of view when we define our orbits, when we design the missions, because we have more accurate measurements on radiation, on the data, on the magnetic field, on variability. After Juno, of course, we will have in our hands a big set of data able to provide us a complete picture from the technological point of view. From the scientific point of view, the list is infinite, because the questions, I mean, the answers we got to some of our questions really open new questions. Because, for example, this issue with the iotail is really a big question. To understand the details of the Alvan interaction with the ionosphere of Jupiter, and try to understand why there is this form, and why sometimes there is this double tail and some other observations not. And this opens a big, let's say, link also with the plasma physicist communities, because this is a natural laboratory under extreme conditions. So this is what we learned, and what maybe creates us more curiosity when we have to plan other missions of this type, for example, in other planets. Because we will be, let's say, more prepared to see things like the ones we saw in Jupiter, or not to see them, and in such a case to try to understand why. Of course, another challenging story for exploration is the story of the ice giants. I didn't have the chance to talk about this in this talk, but these are environments that are really interesting from a scientific point of view, since we have magnetospheres that are completely different with respect to what we know, what we are used to from the Earth case, from the Saturn case, from the Jupiter case. And there are configurations that depend, for example, on the epoch that we will have when and if we actually go there. That we have configurations, for example, where solar wind enters completely on the open field lines regions, or the opposite. And these are places that really we do not know how they work. So all this experience from Jupiter will help us to be better prepared also for different concepts and more exotic stories in the near future of exploration.
Okay. Thank you. So if there are no more questions, unless this is your last chance, so this is coming to an end. So again, thank you very much. Thank you so much, Christina, for a nice talk.
For being here.
And let me just remind everyone that next week we continue. There will be a talk given by Norbert Jakowski on the impacts on GNSS. So we're going back to the Earth. And there will be 2 more talks before we finish this series on risk associated with the space environment. So you're always welcome to join and to listen to the talks that are also on the EC website. And if you have questions, please don't hesitate to interact with us. So again, thank you very much for attending, and hopefully see you next week. And thank you, Christina.
Thank you all very much for attending, and thank you, Thierry, for the invitation. Thank you.
Bye-bye.
Bye-bye.